Today, talking about our forces, really trying to make sure we reviewed and found those forces, talked a little bit about the wheel and the relationship. I did make a quick edit there and showed the little red bar so it continues through, right? It's nice and continuous, which you'll see was a horrible edit here in just a second. But the idea is that we need to be able to look at a compound, a molecular formula, determine what types of bonds are present. Once we know the bonds that are present, we can then determine the types of forces that are present. Once we have the forces, we can predict intermolecular things, like your phase transitions, melting points, boiling points, vapor pressure, and solubility, which we will look at today. So how do we apply that knowledge? So there's the horrible edit. So what I believe we went through and ended on Tuesday, was that we looked at 4. Right? And the short of it is that we recognize that we have a polar covalent bond between the oxygen and the hydrogen, which would lead to which force? Which force? Specifics. Dipole-dipole. Because I have a dipole-dipole force, now I can evaluate further on and say, do I have a hydrogen bound to oxygen, nitrogen, or fluorine? Yes, which means hydrogen bonding. Okay? So I've ignored pretty much the rest of the molecule. Okay? You should be evaluating that with a little bit of practice. You'll start to recognize that you need to be looking for those polar covalent or ionic bonds. Those are the important bonds. The non-polar covalent aren't all that useful. Okay? So you start to zero in on the effectively weakest bonds. When we look at 4b, hopefully what jumps out immediately is the presence of sodium. And why is sodium a special thing to look at? It's a metal, which means with the presence of a metal and all of these atoms being nonmetals, we know we have what type of bond? An ionic bond, which means what type of force? Ionic or electrostatic. And all I'm going to do is do elect. Okay. Which force is stronger, ionic or hydrogen bonding? Ionic. So because the ionic is the stronger force, what is that going to do to the energy necessary to rip apart individual molecules of 4b from each other? It needs a higher force, okay, which means a higher temperature. A higher temperature means a higher melting point and or boiling point. Make sense? Yes? Prove it. You got 1, 2, 3. I would recommend starting in reverse order. Start with 3, 2, 1. Go through and evaluate each of those structures for the types of bonds that are present, what force that would lead to, which force you should be comparing when you compare each of those molecules, and decide which one of those has the higher melting point within each number. Okay, so this is 3 separate questions. Anybody have any questions about that? Ness first, because I saw a hand.
I think I missed it. How do you tell which one is the higher melting point after you
So the higher melting point is because it's going to have a stronger force. So we have to add more energy in to break apart that individual force. So the stronger the force, the higher the melting point. There was an
We're comparing A versus B.
Yep, A versus B. So 1A versus 1B, which one has the higher melting point? 2A versus 2B, 3A versus 3B. Again, 3 is easier than 2, 2 is easier than 1. 1 is absolutely the hardest. We'll see what you guys can come up with, and we'll talk about that one. And Ness, you got another question?
So we're basically looking for which one has the weakest bond.
I won't answer that, but you got a right idea. So we'll go through for 3, and we'll show all the gory details of the work behind what you should be thinking about. All right, so our first approach, we need to define what bonds are present in each of these molecules. All right? We've defined bonds before. Bonds are a connection between any 2 atoms. All right, so when we look at that molecule, we need to be able to look at that formula and say, these bonds are present in that molecule. Right? So in talking with somebody else, they noticed that there's an OC bond and there's a CH bond. There happens to be multiple of those, but I don't care. All I'm looking for is the one type. Right? Does anybody see any other types of bonds present? Right, where do you see the OH?
On the 3B. On the right.
I'm only looking at 3A.
Sorry.
That's my bad. 3A, do you see any other types of bonds?
OH bond.
Okay, and really what I'm fishing for is an OH bond or potentially an HO bond. Okay? Because some people see that and we need to address that and fix and make sure that that's invalid.
Structure carbon is going to be your central bond.
There is no HO bond, right? Okay? And I'm seeing a lot of head shakes yes, and nobody's saying, like, no, I think there is one.
No, I think there is one.
No, you think there is one. Okay, so let's take a look. Remember when we talk about Lewis structure, and this gets a bit dicey and kind of frustrating in my opinion, when you did Lewis structure, you're responsible for taking that formula and converting it into a Lewis structure. So we've got our oxygen, carbon, carbon, and then our hydrogens get scattered on the outside. How would we know that by looking at that formula? Does your silence mean you don't have an answer? What do you got?
Carbon is the least electronegative, so then that would be your center point for the structure.
Okay, so what he's suggesting is that carbon should be the center atom. When you look at this, would you say carbon is the center atom?
No.
Okay. Damn it. Any other thoughts?
The way it's written.
What's that?
The way it's written.
Okay, so there's really two approaches to how we would nail this down. Number one, the way it's written. Okay? We're writing it out in a way to help you go to that conclusion, to that structure. Because that formula could have written, Jiminy, C2H6O. Would you be able to draw that exact same formula as easily? No, and in fact, in that structure, you probably would have drawn a bunch of other variations using that formula. For instance, that formula also matches that compound. Right? So we can't give you just a raw formula. We have to give you some kind of structural information. That structural information is what we're giving you by breaking it out in this grouping. Carbon is next to 3 hydrogens. How many bonds should carbon have? Well, how many electrons should carbon have around it? 8, because of the octet rule. If I put 3 hydrogens around it, how many electrons would it have? 6. Don't open that. Okay. So if I drew that around and just started left to right on this formula, right, carbon with those 3 hydrogens, it would only have 6 electrons around it. Well, it needs 8, which means there has to be another bond, right? What should that other bond be to? Should it be towards the other carbon? Or should it be towards oxygen?
That's nice.
I should draw it towards oxygen. Why should I draw it towards oxygen and not the carbon?
Because it's written that.
Because the way the formula is written is showing me that connectivity. Okay? If we look at the other formula, what should my carbon be connected to? Another carbon. The formula is trying to give me that information so that I can come to the correct conclusion. How many electrons should be around oxygen? This one gets extra tricky. So let's skip that one for the moment. Let's look at the other one. There's our carbon out to 2 hydrogens. How many electrons should be around that second carbon? 8. Does it have 8? No, so what has to happen? I have to have another bond. What is that other bond to? The oxygen. Okay, so now we're at the same spot in both cases where we're going to run into a bit of an issue. What is that bit of an issue? There should be 8 electrons around the oxygen. So we might immediately go to, well, there should be 4 bonds. That's not going to work, okay, particularly for the second one. Because how many atoms are left? Only 1. Which one am I at? Yeah. I can only show that 1 bond. Shouldn't oxygen have 8 electrons around it?
Yes.
Yeah, so what's wrong?
You didn't put all your valence electrons in.
Okay. In this approach, what did I not consider? Remember, when we started Lewis structure, what is rule number 1?
Figure out how many valence electrons.
Total all the valence electrons in your structure. Carbon comes in with 4. There's 2 of them, so we get 8. Plus hydrogen has 1. There's 6 of them. Plus oxygen has 6, which gets you a total of 20. If we look at the current structure on the right, we've got 2, 4, 6, 8, 10, 12, 14, 16. That looks really ugly, but I was just trying to mark them. Okay? I only have 16 electrons shown. I need 20. Where do those last electrons go?
2 dots on top, 2 dots on the bottom.
Does oxygen have 8 electrons? Yes. Kind of, sort of?
Sort of, kind
All of those kind of pieces we've kind of said you're semi-responsible for. Okay? So I would argue the one on the right as a Lewis structure becomes a little bit easier to interpret than the one on the left. Because we look at the left and we say, well, I need 8 things around it. The only thing immediately shown next to it would be carbon. Which means what should I be drawing to that oxygen? Carbon. Well, I need 8 things around it. Can I draw the hydrogens connected to the oxygen? No. Why not? Because those hydrogens are drawn next to the carbon, which means those hydrogens have to get drawn onto the carbon. So what happened to the oxygen? That oxygen, if we go back and look at our total valence electrons, we haven't accounted for the proper number of electrons. There's 2 lone pairs on it. Everybody kind of get it? Right? So the reason why I wanted to go through and do that, and I know that was painful, and that's a little bit harder, look at your formula, read it left to right, and try and piece it together carefully. There is no HO bond because the hydrogens are all bound to the carbon. Yeah? So the bonds that are present in 3A, OC, and CH. And that's it. So far, so good? Okay. So I might need to get rid of that formula stuff at the bottom. Whoops, but not all of that stuff. Okay, what kind of bond is a CH bond? London dispersion is not a bond.
Sorry.
It is a non-polar covalent bond. I'll get to you in a second, so still don't answer that yet. Okay. What is the OC bond? That one is admittedly harder. Is it an ionic bond? No. Why? They're both nonmetals. Is it a non-polar covalent bond? No. Why? It's not same atom to same atom, and it's not carbon to hydrogen. So if it's not ionic and it's not non-polar covalent, it is polar covalent. A non-polar covalent bond gets us what type of force? London dispersion forces. A polar covalent bond gets us dipole-dipole. Okay. What happens with the second compound? What are the bonds present? OC, CH, OH. OH, OC, CH, CC. What kind of bond is a CC bond? Non-polar covalent. What kind of bond is an OH bond? No. Try again. What kind of bond is an OH bond? It is a polar covalent bond. Hydrogen bonding is not a bond. Stop listening to biologists. Okay? It is not a bond. Okay? It is an intermolecular force. It is a horrible name. I will absolutely grant you that, but it is not a bond. Okay? What kind of bond is a CH bond? Non-polar covalent. What kind of bond is an OC bond? Polar covalent. What kind of force comes from a polar covalent bond? Dipole-dipole. What kind of force comes from a non-polar covalent bond? London dispersion forces. What kind of force comes from a polar covalent bond? Dipole-dipole. We'll come back to that in a second. Non-polar covalent? London dispersion forces. Okay. When we hit the dipole-dipole in 3A, we should have talked about it then, and I apologize, I forgot to mention it. As soon as we find we have a dipole-dipole, what should we consider? Is it also hydrogen bonding? To be hydrogen bonding, what must we have? Hydrogen. There's hydrogen in this compound. Does that mean I have hydrogen bonding? To have hydrogen bonding, I must have the physical bond, hydrogen bound to nitrogen, oxygen, or fluorine. Okay? Do I have a hydrogen-oxygen bond? No, which means this one is only dipole-dipole. We go over to the other side, the OC bond at the top. Okay, dipole-dipole. The next one? Yes. Okay, so what do we do with all of this information? What we've done is classified all of the strengths or all the bonds and all the forces that are present in each of these compounds. Kind of the guiding principle behind this is answering what the question was. Well, the question was higher melting point. To have a higher melting point, that means more energy must be put in, which means a higher temperature. Not quite sure what I was writing. Let's do this. Higher temperature, which means more energy. I have to break a stronger interaction. Okay, so a higher temperature means a stronger force. Because I've gone through and classified all of the forces in each of these compounds, I could now go through and deal with this kind of question. I'm looking for the stronger force. In 3A, which force do I want to look at? Dipole-dipole or London dispersion? Dipole-dipole, because it is stronger than London dispersion. Whoa, where's my screen? There it is. Okay. In 3B, which force do I want to look at? Hydrogen bonding. Why hydrogen bonding over the dipole-dipole force? Hydrogen bonding is a stronger force than dipole-dipole. Okay. And we're going to come back to that in a second-ish. Okay. Because I know hydrogen bonding is the stronger force, that means that compound is going to have a higher temperature, which means higher melting point. 3B is my answer. Make sense? Okay. So in doing this, we started with the bonds, so we had to be able to define the bonds. This is what we did back in Unit 2, ultimately with nomenclature. We added a little bit more here by calling them polar covalent. So we added a new bond. Once we had the bonds, we then had to define what force would come from them. Once we had the forces that came from them, we had to know the ranking of which force was strongest or weakest. Once we had that information, we have to know what we're leveling this on top of or what we're scaffolding it. Our question was based off a melting point. That means stronger forces, and now I can answer the question. Make sense? So we've got lots of independent pieces that we're all kind of putting together to get to a final answer. Okay? And a lot of that centers on being able to identify your bonds, identify the forces that come from them. Okay? That is the point of this figure. What are your bonds? What are your forces? The bonds tie to the forces across the figure. Okay? This also shows something about strength of force, and unfortunately doesn't show strength of bond quite as cleanly, and I need to make some edits to this. Okay? The strongest force is which? Ionic. The strongest bond? Covalent. It goes the opposite direction, because remember, this is cyclic. It folds back on itself. Kind of, sort of.
So you said ionic bond is the strongest force?
Strongest force, weakest bond. Okay? So for 2, what do you see as the strongest force in 2A? I heard 2 answers. Heard CH and CC. Both of those are the actual bond, not the force. So the question shifted. I showed you a bunch of work for 3. I showed you a little bit of work for 4. Now I'm not asking for any work. I just want to know what the force is. What is the strongest force in 2A? London dispersion. Okay, why? Well, the CC bond is nonpolar covalent, which gets us London dispersion. The CH bond is nonpolar covalent, which gets me London dispersion. Right? So internalizing that to then get to the conclusion that the strongest force I'm going to look at for that is LDF is where you should be, at least eventually. Okay? And by eventually, I mean by Thursday, like not next Thursday, but the following Thursday at 7 a.m. That's where you should be. Right? Those of you who are missing that, that's the final exam. What about 2B? Dipole-dipole. Why? Okay. I have the OC bond, which is going to get me a dipole-dipole. Which is the stronger force, dipole-dipole or London dispersion? Dipole-dipole, which means this one's going to get me the higher melting point or boiling point. Make sense? Okay. So 1. Which one has the higher melting point? What's the strongest force in 1A? A London dispersion force. What is the strongest force in 1B? London dispersion force. Which one is the stronger force? London dispersion or London dispersion? They're the same, so this becomes difficult. We'd have to evaluate the next step. Right? Because my analogies always go weird and haywire, we'll tone it back a little bit, and instead of a Tyrannosaurus Rex, you get to fight me or a 2-year-old. You're probably going to fight the 2-year-old. Why is that?
Because I have experience with 2-year-olds.
You have experience with 2-year-olds. You could probably deal with a 2-year-old instead of me. Right? But what if instead of me versus 1 2-year-old, you have to fight 1,000 2-year-olds or me?
I take you.
You'll probably now start taking me on, right? Because you might be able to take care of 10 2-year-olds at once, but 1,000, minimally, you're going to get worn down. You may be able to take out a large percentage of them, but eventually,
Take them at the knees.
you may just be suffocating in babies. And yeah, that's not going to work out so nicely for you. So you might now shift your perspective to look at me. The same thing is happening here, okay, sort of. Okay, because here, strength is now irrelevant. Okay? 2-year-old versus 2-year-old, there's no difference. But 2-year-old versus more 2-year-olds, well, why does 1B have more 2-year-olds? There's more compound there, which means there's more surface area to interact. When we're talking about chemistry, it's how things interact with each other. If it's a larger thing, it's more likely to interact. There's more surface area for that interaction to happen. Which means even though it's a weak force, that weak force is now compounded. And I get a larger amount of it, and 1B ends up having the higher melting point. Make sense?
Would carbon to carbon be stronger than carbon to hydrogen because the electronegativity is smaller?
Yeah. It would be a more nonpolar covalent bond. Right. So does anybody have any potential questions that now might be popping up in your head? Okay, well then I'll ask the question. Which has the higher melting point? Which has the higher melting point?
So at what point does surface area be? The surface area is huge.
At what point does surface area overcome the strength of the force? That's a good question. Okay? It's one that we aren't very good at answering yet. Okay? We come up with approximations and guesses, but ultimately those guesses we have to test. Okay? So would you be expected to answer this question? No. Stick with the forces. That's where your happy place is. Make sense? Okay. So phase transitions, we just talked about quantifying these. Let's take a look at a quick diagram to represent this, sort of this. I'm going to put a pot on the stove. In that pot, I'm going to have a bunch of ice. I now measure the temperature of that ice. What would my temperature be? Okay, probably something in the negative Celsius degree range. We're looking at a very low temperature. Okay, so let's say negative 5 degrees Celsius. I now turn on the stove and start to heat it up. What happens to the temperature of that ice? It rises. Okay, until eventually what happens? It starts to melt. What happens to the temperature? It's at 0 degrees Celsius. There's still ice present because it's still freezing, right? But there's also now liquid water present because it's starting to melt. What happens to the temperature? It's still trying to convert the ice over to liquid water. I have to add enough heat to force that to happen. But I can't be higher than 0 degrees Celsius, because if I'm higher than 0 degrees Celsius, what happened to my ice? It's all gone. So what happens to the temperature as I add heat? It stays the same. It plateaus at 0 degrees Celsius until what happens? All of the ice is turned into liquid water. Now what happens is I continue to add heat. Now the temperature will start to rise again until what happens? It starts turning into a gas. Okay? Because I have both liquid and gas present, okay, I can't be higher than the boiling point. So I would be at 100 degrees Celsius. What happens as I continue to add heat? The temperature again doesn't change and we get another plateau until eventually what happens? All of the water boils technically into a gas, and now in the gas state I can continue to add heat. So this is why when you see lines saying caution, steam, right? It goes, oh, steam, it's just 100 degrees Celsius, it isn't that bad. 100 degrees Celsius is pretty bad, right? But more than likely it's not 100 degrees Celsius steam. It's probably a lot hotter than that, right? Because I can continue to add heat to that gas, and what happens to the temperature? It continues to rise, right? And for the sake of this class, it would continue to rise indefinitely, which means I could get million-degree water or steam, right? That would be insanely dangerous, right? We see these plateaus for phase transitions. Since we're only concerned about solid, liquid, gas at this stage, those are the only transitions we see. Okay? Kind of makes sense? So this is just a phase diagram. What we're talking about is what happens with the heat in each of those cases. When we transition between a phase, I have to constantly put heat in, but the temperature will not change because the heat is forcing the phase change, not changing the temperature. So heat is doing two things, changing temperature or changing phase. If there's no change in phase, I can change the temperature. Right? If there's a change in phase, I can't change the temperature. That's all this is trying to show. Kind of, sort of? Cool. So let's get back to the forces. Vapor pressure. So here's a fun little question. Already in multiple choice format. Those of you that have started the practice exam, ta-da, practice exam question. Based on the intermolecular attraction, so you're already seeing a tip-off on what you need to be using. You need to be thinking about your intermolecular forces. Okay? Predict which of the following liquids has the highest vapor pressure. This question I particularly like. Most students don't, for the amount of thought that has to go behind this. Okay? What does it mean to have a high vapor pressure? What does it mean to have a pressure? You have a gas. Okay? If we're talking about a vapor pressure, or let's pause on that. Pressure means gas. And yet what are we looking at? A liquid. So that's weird. Are we referring to just a pressure? We're talking about vapor pressure. Vapor pressure is the amount of gas over a liquid. Does that make sense? So we're talking about the highest vapor pressure, which means which of these has the most gas above a liquid? What would cause a substance to be in the gas state instead of the liquid state? Boiling point. Okay? So this is effectively asking about boiling point, but in kind of a backwards fashion. If we said highest boiling point, is that going to work? If we go to a high boiling point, how much liquid is in the gas state? Very, very little, because it's a high boiling point. What we're talking about is gas above a liquid, and I want the most gas. So we can approximate this to mean the lowest boiling point. To have a low boiling point, what do you need? You need the weakest force, not bonds. Okay? We would need the weakest, whoa, that's supposed to be a W. Let's try that again. The weakest force. Okay? To get a weak force, we would need the strongest bond. That becomes a little bit more difficult, so we could instead say our weakest force would be, what's our weakest force? London dispersion forces. So if we can find a compound with London dispersion forces, that would be good. Is London dispersion forces explicitly stated in your answers? No. So London dispersion comes from what compounds? What kind of bonds? Non-polar covalent. How do I know I have a non-polar covalent bond? Same atom to same atom. So same to same and carbon to hydrogen. So to answer this question, we literally haven't even looked at the answers really much yet. Most gas above a liquid means lowest boiling point, which means weakest force, which means London dispersion, which means non-polar covalent, which means I need to find same to same or carbon to hydrogen. All of that thought has to happen relatively quickly. Okay? That's a lot of individual steps to move through. That's challenging. Okay? That's why students tend to freak out at this question. It's also one of the reasons why it's an awesome question, because it really shows an understanding behind it. Does that make sense? So now let's go through. We want same to same and carbon to hydrogen. We're going to start with answer choice A. Okay, why no? You immediately see an OH, so that doesn't work. So answer choice E. You see a sulfur. Okay, what is that sulfur connected to? To carbon and carbon. Remember, this is that CH2 issue. Okay, so carbon to sulfur, is that same to same or carbon to hydrogen? No. D. You see the Cl. Why is the Cl particularly tricky? Okay. I would argue the end isn't that big of a deal, but let's look kind of in the middle. C. Doesn't that look kind of like a Cl in blue? Yeah, except it's not Cl, it's CH. I think Cl is kind of a tricky one because just writing CH looks kind of like that. If you put the Cl at the end, what does your brain start to see? And starts to draw out the rest of that H. Okay, so be careful, particularly with chlorines, because that can kind of mimic. Okay, so watch for those things. So with Cl, what is the Cl connected to?
Carbon.
To carbon. Is that same to same or carbon to hydrogen?
No.
No. C. We see oxygen, which means oxygen to carbon, which is polar covalent, so that didn't work. B. C to C, that's same to same, and C to H, that's also our nonpolar covalent. So our answer becomes B. I did see a little funky face on someone being like, I don't know what you just did. Where's your questions? No questions? They're just like, yeah, whatever. Okay. You got questions? You should talk. Yeah.
Okay, if B didn't exist, what would it be?
Okay. So that's a fun little question. Okay. So for the record, everybody watching at home, he said B didn't exist as an answer. Now, what's our answer choice?
Dipole is your next weakest.
Okay. We'd have to move through our forces. London dispersion is now not our weakest force based off of all of those rankings that we just came up with, right? Everybody agree with that?
Yeah.
Which means the next weakest force would be dipole-dipole, which has to come from a polar covalent bond. Why has that now become tricky?
Because there's a lot of polar covalent.
All of those are polar covalent bonds. So that now becomes a significantly more difficult question to answer. Okay? I would argue in that question, we do a couple things. Number one, you should be able to eliminate an answer right out of the gate. A gets eliminated because we have hydrogen bonding. The OH bond is a polar covalent bond which generates dipole-dipole forces. Because we have hydrogen bound to oxygen, nitrogen, and fluorine, we have hydrogen bonding. Hydrogen bonding is stronger than dipole-dipole. A is wrong. Okay? CDE. Good question. I don't know either. Okay? Which ultimately means wouldn't be asked. How could we change so that I could ask the question getting at this point?
Lowest vapor pressure?
Switch the question to lowest vapor pressure. By now being lowest vapor pressure, what does that mean for boiling point? Highest boiling point, which means strongest force, which means ionic. There's no ionic, so we'd move to hydrogen bonding. There's A. Does that make sense? Okay. For those more advanced questions of where things start scaffolding, when you have to kind of rank things out like that, that is fair game in organic chemistry, and even then we kind of have to play with it a little bit. I don't want to open the can here. Okay? And I'm hoping nobody else had questions after that, because I just deleted all the work. We're good? Okay. So, the next fun one, solubility. We've talked about solubility before, right?
Yeah.
Okay. In reference to what? Solubility rules, what did you say? Solids and liquids. This still deals with solids and liquids potentially. Solutions, getting at a better reference. Compounds. What kind of compounds? Because those are all compounds too. Okay. As a hint, check out the lower right-hand corner. When we're talking about solubility of compounds, notice the examples we're referencing up here versus the compounds being referenced down here. What's the difference? Ionic versus covalent. Do we have a rule set for ionic compounds? Yes, that's our solubility rules. Okay, so when we're talking about solubility and miscibility, what we're talking about is the mixing of covalent compounds, not ionic compounds. We have a different set of rules for ionic compounds, and we can talk about why they would dissolve using forces as an interaction. Okay? But that gets slightly outside of the scope, so we'll kind of deal with that when it comes. Okay? So our primary focus here for solubility is talking about covalent compounds. Okay? Because I can't look up the solubility rules for water versus ethanol. There is no solubility rule for that. Okay? I have to use some other process. That some other process is looking at forces. Okay, so solubility, the ability for anything to dissolve in a liquid, solids and liquids. Miscibility is the ability for any liquid to dissolve in a liquid. Okay? Believe it or not, gases are classified as liquids in this case. Okay? The rule of thumb that usually gets kind of spit out, which you've probably heard in other cases, would be like dissolves like. Well, what the hell does that mean? Like what dissolves like what?
The same thing dissolves the same thing.
The same thing dissolves the same thing. Is water the same thing as ethanol? No, so that means they don't dissolve because they're not the same. Would it even make sense to say water dissolves water? I mean, those are the same things. No, that's kind of a silly statement to make. Water doesn't dissolve in water. It is water. Okay? I don't want to open that one yet. So what I've modified within the rule set is the context of what like dissolves like is referencing. Like dissolves like is referencing the forces. So what I want to go through and do is look at the two compounds, and I want to determine what forces are in those two compounds. Once I know the forces, I can then compare those forces and say, are those the same or are they different? If they're the same, well, that's like dissolves like. What if they're different? They don't dissolve. All right, so let's go through and take a look at the first one. What force would you get from water? Hydrogen bonding. So this is the one case where you could jump straight into hydrogen bonding. Why could you jump straight in for hydrogen bonding?
Because there's only the one.
It's the question that I asked. What question did I ask?
What force?
What force? That's why you can say hydrogen bonding. All right, so we get hydrogen bonding for water. What force do we get for ethanol? Okay. We also have hydrogen bonding and LDF and dipole-dipole. All of those forces are in that compound. Of those forces, which is the most important? Why hydrogen bonding? It's the strongest. Right? The London dispersion forces is weak. Hydrogen bonding is going to dominate, which means when I now compare these two compounds, I'm comparing hydrogen bonding to hydrogen bonding. Are those similar? Yep. What happens? They dissolve. Okay. Thank you, spring break.
Sorry, why is the middle one dipole again?
Carbon to oxygen.
Thank you.
Yeah, I tried to highlight it.
Which one dissolves in which one?
So the reference of which one dissolves in which is really a reference of an amount. Okay? So when we're talking about solubility, there's the solute and the solvent. The solvent is the one in the larger concentration. The solute is the one in the smaller concentration. Okay? When we look at water and ethanol, I'm pretty sure they're equal solubilities. Doesn't matter which way you go, you get max solubility.
So what would create?
What does water and ethanol create when you mix them? Vodka, beer, whiskey.
Because it says dissolve, so I'm thinking like something happens, it just dilutes itself.
It just dilutes it. Yeah.
It's like
That's it.
ice cubes to your drink.
That would run alcohol.
If you add the ice cubes to vodka, sure, I'll accept that one, yes. Yeah. Okay. What about the second one? Okay. What is the strongest force in water? Hydrogen bonding. What's the strongest force in propane? London dispersion force. What do we expect? Those are different forces. They don't dissolve. Okay? Are there gray areas? Hell yeah. Don't worry about it. Okay? Because what we will test you on is the non-gray areas right now. Okay? Just to be a jerk, because we know I can. Let's tweak this first one. Did I change any of the forces?
No.
No. So what do you think? Should water dissolve in non-anol? That was kind of a fun one.
Will it depend on how much water you have?
To a certain extent, but for the most part not in this case.
I have no idea.
Still yes.
No, this one won't dissolve. Why not? There's too much London dispersion. So now in this compound, the London dispersion overcomes the effect of the hydrogen bonding. That molecule is mostly London dispersion force, doesn't mix with the water.
So that's great.
Okay? This would be that gray area question. Okay, so this is why I asked, threw it out there, is let's be a jerk, let's talk about it, and let's think about what's going on. Okay? That line, how many non-London dispersion forces do you need to overcome hydrogen bonding? Again, okay. Okay? But I want you to be at least aware of it and thinking about that aspect. It's not just the strength of the force, there's other contributing factors, like the amount of the force.
What if it was, if you were trying to mix it with the propane? Then,
So in this example, and we've gotten a couple questions on this that are referencing the amount of each substance into it. In this case, we're ignoring amounts. We're just saying it either is or it isn't, period. Okay? Because we can change systems to force these things to happen. Okay? For instance, what could I do to the temperature? Potentially increase or decrease it, depending on what I was trying to do. Okay? And the physical states of each of these substances. Kind of, sort of? Okay. So, strength of the force is our dominant factor. That's the thing we want to consider. When we move to our ionic compounds, the strength of the force in the ionic compound will be strong, fair enough, ionic or electrostatic, and that for water will be hydrogen bonding. Are those similar? You're saying no. Really? A yellow hydrogen bonding isn't similar to an orange ionic force?
no.
Okay. Just because the names aren't the same doesn't mean it doesn't mix. That again kind of hits this weird gray area. With ionic compounds, we add a whole nother level to it. That level we actually already talked about, though I haven't drawn it here. When we look at water, there were two aspects to it. Okay? We had the partial negative charge on the oxygen, and we had the partial positive charge on the hydrogen. If I drew in chloride now, chloride being negative would generate an interaction between the hydrogen and the chloride. That single interaction is not going to overcome the interaction between sodium and the chloride. Why not? What is the green interaction versus the black interaction?
Ionic force compared to hydrogen bonding.
Okay, this is an ionic or electrostatic force versus, arguably it's not hydrogen bonding. This one gets kind of weird. Okay, kind of dipole-dipole / hydrogen bonding. Okay. The stronger force is the ionic, which means we don't break the interaction between the sodium and chlorine. It stays bound, which means we keep the bond. So why on earth, when I add sodium chloride to water, does it dissolve? Why do we break that ionic bond? Is it just one water molecule? No, it's a bunch of them. The sum of all of those water molecule interactions, while they are weaker, is stronger than the one or two ionic interactions. That's why we can overcome the ionic bond by having a multitude of weaker interactions. Okay? So it's a balance between the undissolved substance and the dissolved substance. We're creating a new state, and that makes it a little bit more challenging to deal with. Okay? Kind of make sense? So, like dissolves like to predict which of the following liquids is miscible with water. Okay? So as soon as we see the word miscible, or actually I would argue we should probably just key off on like dissolves like. And like dissolves like means what are we looking at? Okay? okay, are forces, and in particular the ability for things to dissolve, so solubility. Why did they use the word miscible instead of soluble? Liquid to liquid, so they're being more precise in their terminology, okay, which is nice. They're also probably doing it to trick you, because the odds that you saw miscible and recognized miscible as a word, less likely, right? But we're referencing solubility, okay, and we're saying which of the following liquids is miscible, okay, so that's where we have to be careful. Miscible is referring to what? The ability to dissolve or the ability not to dissolve? This is to dissolve. Okay, what would it be to not dissolve? Immiscible. I-M-M-I-S-C-I-B-L-E. Okay, so we have to reference the question very, very quickly or carefully to ensure that we're answering the question that's asked. Okay? It's like forces dissolve like forces. So I'm looking at two forces. Well, I only see answer choices. Those are the only formulas given to me. What am I comparing those formulas to? To water. Conveniently, not written out as a formula. Why? Again, to mess with your head. To remove some of that contextual information. You have to acknowledge that water is being asked in the question. That is H2O, which means which force? Hydrogen bonding. Because I am looking at the ability to dissolve, I need to find the force most similar, most being the operative word. Because this is 130, our most similar to hydrogen bonding will be hydrogen bonding. And now we could go through and evaluate, right? Just for the record, when we've asked for homework, I've asked you to show work. Most people circle the answer. Circling the answer is not work. What did I just write down? I wrote down the work. That's what you're supposed to be writing down. When else should you be writing that down? When you take the test, right? Otherwise, you're doing those thought processes in your head. Eventually, you'll screw it up, right? If you write it down, you can now grade your own work and potentially catch mistakes. If you do it in your head, you will make mistakes on mistakes. Write it down. Right? So most similar to hydrogen bonding, I would now go through each of those compounds and look for their forces. So based on the first one, I'm not even given a structure. I'm just given a formula, carbons and hydrogens. What would be my force? It can only be London dispersion. Because at best, I have carbons to hydrogens only, which are nonpolar covalent, which are London dispersion forces. I'll also have to have some carbon-carbon in there, which may not be obvious to you. That's okay. Those are London dispersion. We move to cyclohexane. What do we see? Same thing, London dispersion force. We move to chloroform. What do we see? Ooh, there's a chlorine. That's Cl. Okay. For reference, if you see something like this on the final, you can definitely complain and yell at me because I'm the one responsible for trying to put it together and compile it. I hope there won't be any typos. I apologize right out of the gate if there is. Okay. Officially, to clarify this, that 3 should be subscripted. If you see something like this on the exam and you're just like, I can't tell if that's a 1 or a 3, what should you do? Raise your hand, I'll come by and be like, no, that's a CL. The 3 should be subscripted, and I'd probably write it on the board. Okay? If you don't ask, I can't help. Okay, so that's Cl3. Because we have a chlorine, what do we have? Ionic. When do we have ionic? Metal and a nonmetal. Is chlorine a metal? Is hydrogen a metal? Is carbon a metal? Do we have ionic? No. What do we have? We have a polar covalent bond. The polar covalent bond leads to dipole-dipole. Do we have hydrogen bonding? No. To have hydrogen bonding, I need to have a hydrogen. I do, bonded to oxygen, nitrogen, or fluorine, which isn't listed there. So I have a dipole-dipole. Okay? Ignore all the other answers. We only had A, B, C. What's your answer? Why C? Dipole-dipole is the most similar to hydrogen bonding. C becomes the answer. Don't circle C right now, because that wasn't, we had other answer choices, right? Okay. We just want to put it out there as an option. I think I saw somebody with a question maybe. Is there a question maybe out there? No? Okay, next one. Glycerin, what do you see? Okay. Explicitly shown OH, okay, which is nice because if they'd written this out in the standard chemical formula, we wouldn't know if it was an OH or an OC bond. Okay? So they wrote it out as OH, which means hydrogen bonding. Okay? We're again skipping a step because officially the OH is a polar covalent bond, which is dipole-dipole, which is hydrogen bonding because hydrogen's bonded to oxygen, nitrogen, fluorine. Okay? Hydrogen bonding, is that similar to hydrogen bonding? Yeah, so that's probably our answer. Let's go ahead and take a look at toluene. What do we see for toluene? We see CH, non-polar covalent. We also see this CH3 set out differently. Why? Who freaking knows? They changed the order and how each of these things are presented. But anyway, you slice that one. It's London dispersion forces. Okay, make sense? We good? Okay. Yeah, we'll do it here. So there's a question on the practice exam asking about the ability of CO2 gas to dissolve into water. So if we were to write this out as an equation, CO2 gas plus water liquid equals CO2. It's dissolving, so it's not changing the compound. It's changing the phase. It would make it aqueous. Okay? Plus still H2O liquid, right? Okay. We could also look at the compound sodium chloride, which is a solid dissolving in liquid water. This one's a little bit different, but let's just keep it simple. Sodium chloride, aqueous, plus H2O. Everybody okay with those two equations? Okay, so let's address some things. What might be different about the top one from the bottom one? Insanely vague. One's a gas and one's a solid. Yes, I wanted more than that though, I apologize. Okay, ionic versus covalent, also useful. Didn't think of that one, keep going. Is there more information available to you for one of these phases than another one? More information you should be evaluating, let's say that. STP. Okay, what are you talking about when you're talking about STP? Standard temperature and standard pressure. When we look at a gas, pressure and temperature are important. When did we talk about STP? With gases. Did we talk about it with solids? No. Do I need to worry about pressure for the second one? No. Pressure is entirely irrelevant to the second one because not a gas. Okay? The first one, pressure is going to be important. Okay? Let's address first the temperature, though, before we even deal with pressure. Okay? To get this solid to dissolve into water, what might I do to temperature? I would increase it. Why do I want it? Ignore that. To the first one, CO2 and water. What would I do to the temperature? I would wait, you just said decrease?
Yeah.
But the second one was to increase. Why is the first one now decreasing?
Because you want to mix with liquid and to get
Gas versus solid. When we move from the solid to the aqueous, I'm effectively converting the solid into, it's not a precipitate because a precipitate is a solid. If I convert the solid into being dissolved, it's now effectively a liquid. What do I need to do to temperature to force the solid to go to a liquid? Heat it up, increase it. Let's take a look at the first one. I'm taking a gas and I'm turning it into Aqueous, effectively a liquid. What should I do to the temperature to cause a gas to go to a liquid? Decrease it. By coming up with those ballpark approximations, we can see why the temperature dependence is different for those two phases. You're looking at the beginning to end transition. Make sense? Okay. Let's think about pressure for the top one. Okay. Should I increase or decrease the pressure? Okay. What happens if I decrease the pressure? So I've got my container here, okay, with my liquid in it and my gas floating on top. If I increase the pressure, decrease the pressure, what am I doing?
Temperature drops.
I'm doing more volume, so we could do that, but I don't even want to change the volume. How would I decrease the pressure of the gas without changing volume?
Drop the temperature.
Ignoring temperature. What determines pressure?
Increase the water.
The amount of particles impacting the walls, right? So if the pressure decreases, and I'm not changing the volume or the temperature, what happens to the amount of particles?
Fewer particles.
I have fewer particles. If there's less particles, am I going to be able to dissolve it more?
Yeah, no.
There's less stuff there. Can I put more things into the liquid? Okay. If I had more money, I could probably give you all more money. If I had less money, can I give you more money?
Hopefully.
Okay. If we start with less gas to begin with, it's harder to put the gas in. Okay. What happens if we increase the pressure? What would happen to the number of particles? They would increase. And they're now starting to fight against each other. What do they want to do? They want to get as much space as possible. They want to get away. Where could they get away to?
Into the water.
Into the water. So if we increase the pressure, we can force those gas particles to go someplace they may not want to, into the liquid. So by increasing the pressure, we can force the gas particles into the liquid. If we decrease the pressure, what happens? The gas particles are like, well, I'm going to go where there's less stuff. And they're going to move up to the outside. Right? Which you can see sort of effectively with soda cans if you leave them in your car during the summer.
Even just those water bottles with straws. Fill up your couple.
You will start to see explosions. Why? As you're adjusting the temperature, what happens to the pressure inside the can? It increases or decreases depending on our temperature changes.
So it explodes
Okay?
either way.
So it would explode.
Either way, if it's
Yeah.
hot or cold. They explode in freezers too.
In freezers, it's a different issue. In freezers, it's not a temperature thing. It's a secondary issue, so don't open that one yet either. If you want to talk about me after class, we can. Okay. So we got a little bit more that I want to talk about. We look at these three compounds. Which one of those should immediately jump off the page at you? First, second, third. Third. Why? It says aqueous, and it has a hydrogen in front, which means that one is an acid. We should recognize that one right away as being dangerous because we know nomenclature to say that that's an acid. The other ones we may be less concerned about immediately. They're also pretty dangerous, but okay. We have a nomenclature system for acids. That's because acids are really important. What's the important part of an acid? The hydrogen. How do we know it's the hydrogen? We put it in front. Okay? So that's our working definition with acids. We'll pick up there on Tuesday. We will probably finish everything Tuesday and just be talking about review.